Thanks for joining us in this optimization workflow. This is part 2 in a 5-part series. If you have not watched part 1, it will give you a full overview of our workflow using Siemens SimCenter 3D and the value-based tokens to access the design space exploration solver. As a reminder, in this series, we will be looking to optimize a part that looks something like a leading edge rib for a lightweight solution without compromising the structure. In this video, we're going to work on a part file. We'll walk through removing the blends and any unnecessary holes. We'll create a mid-surface mesh, and we'll set up the thickness changes for the web, as well as position changes for the stiffeners in the FEM file.
So this is SimCenter 3D, and the first thing that we'll do is we'll create a new PRT file, and we'll put it in a folder where we're going to store our study. We'll create it, and then we'll save it in our working directory. So we'll work with geometry, and we'll import a parasolid file. So this parasolid file does not have history or feature-based modeling. So you'll see there's no items here. It's not parametric. It's just the common transferred file format. Think of step file. So we can create parametric features, and we do this with synchronous modeling. And the first thing we're going to do is we're going to delete these blends. Since we're doing a mid-surface mesh, so we can select them quickly by just picking a blend size, and it will go pick all the blends that are within our size threshold. You'll see there are a couple here that it doesn't pick, and we want that to be true because we want to have thickness transition areas here. So this is what we want. Put OK, and our blends are removed. Next, we want to delete holes that aren't necessary for our solution. We'll change our filter back over here to faces. Choose exact match, and it's going to find everything that matches those holes, and it's going to delete them. Okay. So we are in the application modeling now. So what we want to do is we want to plan ahead and create expressions, which are going to be our variables using heats are going to change our position of our stiffeners, as well as change the thickness of our web. So we're going to have 3 stiffeners, so we're going to create 3 variables. One's going to be L1, L2, and L3. This is going to be the length that we move stiffener 1, 2, and 3. We'll start with a very small value for each of these. Just move it 1,000th of an inch. And then we'll add one more for thickness change. And this will be for the thickness of the web. So with the synchronous modeling, you can move a stiffeners by both faces, or you can see both of these faces are going to be offset in this direction by whatever value we choose here. This is going to be our first stiffener, so we'll set a formula equal to L1, first stiffener. And we'll hit OK. And you can see it's now building our feature-based history tree. The second we'll do this 2 more times. Allows us automatically pick other faces, just saving time in our workflow. We'll set that equal to our L2 distance and hit OK. And then we'll move our last face. Pick our offsets and set that equal to L3. So one thing that you want to keep in mind when you're thinking about this is what is our range of variables? So if we move this stiffener, we can move it a finite distance before we're going to be outside of our part. So we expect if we move it too far, the geometry is going to fail. Similarly, this is going to interface across this penetration, as well as this is going to interface the side apart. And then we could also change our thickness so that there's no thickness left. So that doesn't mean we can't. We need to always have valid geometry, because heads, if we do input a variable range and for some reason the combination of variables produces an invalid geometry, it won't stop the optimization. It will just produce an error design, and then it'll move on. So he will learn that this combination of variables will produce an error design. So next, we're going to offset the thickness of our web. All right, so now if our arrow is pointing up, so we need to reverse it. So we want to remove thickness that's going to be equal to T1. So if I zoom in here, you can see that this is going to be offsetting this face towards the exterior. And each time it updates, it's going to either add or remove thickness based on our value. And in our case, adding a positive value is going to be reducing the inside face thickness. So now we have our geometry idealized, as well as our parameters that are going to be set up for hues to move our stiffeners and change our thickness. So we'll save this. And the next, we'll move from our modeling application, thinking next. Now pre-post and think Simpson 3D. And down here, we've got a simulation file navigator. And you'll see that hierarchy being built down here. The first thing we want to do is we're working on our PRT file still, and we want to create a mid-surface from the face pairs. We pick our body, and this is a very robust mid-surfacing tool. And it also does two things besides just creating the surface. It creates automatic thickness transition regions, and it remembers the thickness that it was based off of. So we can use that to define the thickness of our finite element models. So we hit OK, and we'll save that as our mid-surface part.
This concludes part 2 of our design space exploration workflow demonstration. Please subscribe for access to the playlist and for easy navigation to the other videos in this series. Thanks for watching.